Hey guys, in this video, I want to talk to you about how do we figure out our Ecell? Do we predict if it's going to increase or decrease? Or how can we calculate that if we have non-standard conditions? Now remember, standard conditions are when we see the little not symbol like we have here. When we have standard conditions, we have 1 atmosphere, we have 298 Kelvin, and most importantly, we have these concentrations of things that are in our beakers to be 1 molar. If we do not have the concentrations to be 1 molar, then we have to do either a qualitative or quantitative approach to figure out what the Ecell actually is going to be. So let's talk about both of those approaches. Most of the time when you're working multiple choice, they'll just have you predict what's happening to the Ecell. Will it increase or decrease, not give you a numerical value. So if that's the case, we can use the approach of Le Chatelier. Now I wrote this in cursive because it's all fancy in French, okay? Now, what does Le Chatelier actually mean? Le Chatelier means that if I apply a stress on a reaction, that reaction will either shift to make more reactants or shift to make more products in order to alleviate that stress. So we have to ask ourselves, what is this stress going to be? Well, the stress is going to be changing those concentrations from 1 molar. We could either increase the concentrations from 1 molar to make it higher, or we can decrease the concentrations from 1 molar to make it lower. So when we go and we calculate our standard Ecell and we're plugging in those standard reduction potentials, we are assuming that the concentration of the aluminum here is 1 molar and that the concentration of the manganese here is 1 molar as well. Now, why I'm putting the 1 molar underneath the things that are charges is because these are your things that are aqueous. Those are your solutions. The aluminum here is your metal, your electrode, and the manganese here is your metal, which is the electrode. So it's very important to know that when I'm changing concentrations, I'm changing the things that are aqueous in our solutions, so I have to look at those. So if I say that this is 1 molar and 1 molar, we have standard conditions, and that is why we can calculate our Ecell at standard conditions by saying Ecell is equal to the Ecell of the reduced species minus the Ecell of the oxidized species. But let's change it up a little bit. Let's say that instead of both of these solutions being 1 molar, that I have increased the aluminum's concentration to be 2 molar. What will happen to the new Ecell value? Will it be higher than 0.48 or will it be lower than 0.48? So this is where we use Le Chatelier. Now, when we use Le Chatelier, this is kind of just a trick that you use. I figure out what is changed in the reaction. So what I have changed is this aluminum right here. What did I do to that aluminum? I increased its molarity because now it's higher than 2 molar. So I look at aluminum and I say, okay, I applied a stress to the aluminum 3+ in the reaction, and more specifically, I increased that concentration that I have there. Well, now, due to the definition of Le Chatelier, if I apply a stress, this is my stress, my reaction will shift either to the reactants or to the products in order to alleviate that stress. If I cause an increase on one side of the reaction, what's going to happen is it's going to cause the reaction to go in the opposite direction. So when I increase, I shift away from that increase to make the other thing to catch up. So increase, I am going to shift away from that increase. And as I'm shifting away, what's happening is I am shifting to the reactant side. And if I shift to the reactant side, what that does is decrease my Ecell. Now, conceptually, why does that decrease Ecell? Is because you're not pushing as many electrons through that wire, because you only push electrons through that wire if you're going in this direction. So if I'm going in the opposite direction, less electrons are being pushed through, and if less electrons are being pushed through, my Ecell decreases. So the rule is, if your shift, this is my shift here, goes in the reactant's direction, then that means that my Ecell will decrease. So let's give another scenario here. Let's say in this case, we are not going to change my aluminum, but we're instead going to change my manganese. So aluminum is going to stay 1 molar, and my manganese is going to increase to 3 molar. So I apply Le Chatelier. I ask myself, where is the stress applied? The stress is applied at manganese. What exactly happened? I have increased the manganese concentration to higher than 1 molar. Well, what will happen as a result? Because this is the stress and I am increasing that, I want to shift away from the increase. And if I am shifting away from the increase, in this case, it's going towards the products. If my reaction shift goes towards my products, that means that my Ecell value will increase. Now, conceptually, why is that the case? My Ecell value is increasing because I am now making even more products, pushing even more electrons through that wire. So if your shift, remember, this is my shift, this is my stress. If my shift goes towards my product side, that will always cause my Ecell to increase. Now, let's do another example. Let's say, let me erase this and kind of fix it real quick. So we had 3 Mn2 plus, and that left us with Al3 plus with a 2 in front of it, plus that. Okay, so remember, we can only apply a stress to our aqueous things. Let's say in this case that I want to change my concentration of Mn to 0.5 molar and leave my aluminum at 1 molar. So where did we apply the stress? We applied the stress to Mn. What happened? That concentration is now lower than 1 molar. So I have actually decreased the concentration of the Mn2 plus. Now, what will happen as a result? What shift will happen? Remember how I said if I increase, I always shift away. So what will happen if I decrease? The opposite is true. If I decrease a concentration, I will shift towards that decrease. So since I am decreasing on the reactant side, I am going to cause a shift towards my reactant side. And that shift to the reactant side is going to cause my Ecell to decrease. Why? Because you're pushing less electrons through that wire. So this is how conceptually we predict what will happen to our Ecell. In this instance, I don't know numerically what my new Ecell will be, but I know it will be some number less than 0.48 volts. Well, how do I get an exact number of my Ecell? How do I figure out quantitatively what my E cell value will be. This is where you have to rely on the quantitative approach, which is the Nernst equation. This equation has not been on the equation sheet in the past. However, I do think that I saw talk with the AP community that they're going to put this back onto the equation sheet. So I will make sure that you guys have it in your new one because that is a lengthy equation to remember. So let's talk about the different parts of this quantitative equation. So this is called the Nernst equation. This E right here stands for your new E cell. Notice how this does not have the little not symbol. That not symbol is right here. So this is the E cell at standard conditions, which is what I would plug in here. This E cell is at non-standard conditions. So we're trying to numerically find our non-standard conditions E cell value. So, like we said, this means E cell at standard conditions. 0.06 is a quantity derived from a more lengthy version of this equation. So just remember that that number is always 0.06. N is the same N that we saw in delta G equals negative N phi. This stands for moles of electrons transferred. And remember, most of the time they'll give you a point just for getting that N number correct. Then we have log, which is a 10-base function. For those of you who are not mathematically inclined, right now it's a button in your calculator. Just know that it's 10-based. And Q stands for something called reaction quotient. How we calculate reaction quotient is we take the concentration of our products raised to their coefficient divided by the concentration of my reactants raised to its coefficient. If you took advanced chemistry last year and you remember K, equilibrium, like Rice tables and stuff, this should look very familiar to you. Q is actually a non-equilibrium version of K, and it's calculated the same exact way. So we plug in our product's concentration and raise it to the coefficient. We plug in our reactant's concentration and raise it to its coefficient. So now that we know the different parts of the equation, the best thing we can do is just try an example problem with it. So let's go back to our very first scenario in which we had the Mn stayed at 1 molar and our aluminum increased to 2 molar. So what we want to do is calculate our new E cell. If I change these conditions, I am now at non-standard conditions. So we are going to plug in everything into this equation. So E cell is what we're finding. E not cell means standard conditions, and so we plug in the 0.48 volts. Now where I got this number is I took the E cell, which from our standard reduction potentials, and I took my reduced minus my oxidized. That's where I got that number. So I get 0.48 volts minus 0.06, you plug that number in, divided by N. So I have to figure out what my N value is here. So if I look at aluminum, I notice that my half reaction for aluminum would be Al, I hope that you guys can see this, to Al3 plus 3 electrons. I also notice that my half reaction for the manganese is going to be Mn2 plus to Mn, and that is 2 electrons on this side. Remember, the way that we find N is we look at both half reactions. So this one has 3 electrons, this one has 2 electrons, and we look for the least common multiple. That tells us how many moles of electrons are transferred totally in the reaction. How many is being oxidized, how many is being reduced. It's transferring from oxidized to reduced. So because 2 and 3 don't have a smaller number that both of them can be multiplied by to equal one another, we are going to have to multiply both of these numbers together. So 3 times 2 is equal to 6 moles of electrons that have been transferred. So that is our N number. And usually we get a point just for getting that correct. Now we're going to take our log function and we are going to plug in Q. When we plug in Q, we are going to use this equation. So we look at our products and we plug in its concentration and raise it to its coefficient. So we would say aluminum 3+, which is 2 molar, raised to its coefficient, which is 2, divided by my reactants, which is Mn2+, which has a coefficient of 1, and it has a molarity of 1 and a coefficient of 3. So when we calculate this and we plug this into our calculator, we kind of want to work backwards to calculate our Ecell. So 2 squared, which is 4, divided by 1 cubed, which is 1. So that would be 4. Then we would take the log of that number. Then we would take the multiplied by 0.06 divided by 6. And then we would take all of that number and subtract it from 0.48. So let's actually do that. I'm going to take some time to actually calculate that out. So let's start here. 2 squared divided by 1 cubed is equal to 4. All right, we're okay with that, right? That's equal to 4. Now we're going to take the log of 4. So 4 log function, that is equal to 0.602. Now we have to multiply this by 0.06 and then divide by 6. So I'm going to take 0.602 times 0.06 divided by 6. And that gives me this number, 0.00602. We are going to take our value, 0.48 volts, and we are going to subtract 0.00602. So 0.48 minus 0.00602. That gives us a new Ecell value. Let me write that in orange. Ecell at non-standard conditions, because you don't see that not symbol, is equal to 0.474 volts. So this is my new Ecell at non-standard conditions. Now, let's think back to what we predicted, right? Didn't we predict that this would increase? I increase my stress, and so I shift away. Because I shift away towards my reactants, my Ecell decreases. So we predicted, using the qualitative Le Chatelier approach, that our Ecell should decrease. It should be less than 0.48. When we calculate it using the Nernst equation, the quantitative approach, we actually do get a number that is less than 0.474, or less than 0.448, sorry. Let me start that over. A number that is less than 0.48 volts, which is true because this number is 0.474 volts. So what we predicted with Le Chatelier is actually validated by the math using Nernst. Now, sometimes on free response, they don't want you to arrive to a final answer. Instead, they want you to predict in terms of Q. So I have a couple of mathematical tricks for you here. All you have to do to answer this question using NERDS is to calculate Q. And remember, we calculate Q with our product's concentration raised to its coefficient divided by the reactant's concentration raised to its coefficient. We did that pretty easily here, right? We said 2, which was our products, raised to the coefficient, over 1, which is our reactant, raised to its coefficient 3. 2 squared over 1 cubed is equal to 4. So we found our Q value. Just by knowing our Q value, we can predict what will happen to our Ecell value. If your Q value is a number that is greater than 1, anytime we take the number greater than 1, we take the log of that number, it will always be a positive quantity. Didn't we get a positive quantity here? 0.602. That is a positive quantity. It's a small quantity, but it's a positive quantity. So if a number is greater than 1, this number was greater than 1, log of Q is a positive quantity. So if we work the math here, if we take a positive quantity here, we're actually subtracting a number from the Ecell at standard conditions. So this, having an answer of Q that is greater than 1, will always cause, mathematically, my Ecell to decrease. So a lot of the times on the free response, they want you to justify in terms of Q. What you need to do, calculate Q, say, according to the Nernst equation, since my Q value is greater than 1 and the log of Q is positive, my Ecell will decrease. Now we're going to do some practice with this whenever we are doing some free response. Now what happens if I get a number of Q that is less than 1? Well, then the opposite is true. If I get any number that is less than 1, and I take the log of that number, any number less than 1, that log of that number is going to be a negative quantity. So let's talk about what if I am subtracting a negative quantity. If I'm subtracting a negative quantity, don't both of those become positive and I'm adding that quantity? So what that means is that my Ecell value is going to be greater than the standard Ecell value. So the rule is, if Q is a number less than 1, log of Q will always be negative, and therefore my Ecell will increase. So I have noticed that a lot of AP readers now would rather you discuss the qualitative version in terms of Q rather than explaining in terms of Le Chatelier. So we're going to do practice with both. This is very easy to use for multiple choice. However, for free response, we want to always refer to Q and talk about the Nernst equation. So we're going to do some practice, and hopefully this all made sense to you guys.